Okay. The title of this presentation is a conservative numerical model for a double fractional Klein-Gordon-Sakharov system. My name is Armando Gallegos, and I am affiliated to the University of Guadalajara in Mexico. This is the schedule of our presentation. I'm going to talk about the continuous model, the discrete model to solve the continuous model, the energy conservation and the boundedness, the existence of solutions, numerical properties, and finally some conclusions. The numerical model that we're going to be talking about during this presentation is this system of partial differential equations. Notice that this is a hyperbolic system. Okay, and we are going to extend this system to the fractional case scenario. So initial and boundary conditions are going to be considered throughout this presentation. The fractional derivatives are going to be understood in the sense of risks. This is the definition of a fractional partial derivative of order alpha of a function u. And the system that we're going to consider in this case is the fractional form of the Klein-Gordon-Sakharov system, which is essentially the previous system of partial differential equations, but we're going to consider an order alpha of differentiation here, an order beta of differentiation here, and both of them are going to be between 1 and 2. So again, we're going to consider initial conditions and the homogeneous Dirichlet boundary conditions. There's an interesting property about Rist's fractional derivatives, that Rist's fractional derivatives are negative operators which are self-adjoint, and thus they have a square root. So this is basically the property I'm mentioning right now, which can be understood as a fractional extension of integration by parts. The system that I presented in the previous page, this system, has a Hamiltonian associated and a total energy. This total energy, as we mentioned in this theorem, is constant. So if U and M are sufficiently regular function, then the energy is preserved throughout time. The proof of this property is by taking derivatives in all the terms. So once you take derivative of the energy, you find this expression which is equal to 0. Okay. The boundedness of the solutions is also an important property of the system. This follows by the Gagliardo-Nirenberg inequality. So for solutions of the initial boundary value problem, there is a constancy such that all of these quantities are preserved throughout time. Okay, I'm going to skip the proof. And one of the corollaries is that the energy is always a non-negative constant. So the purpose of this presentation is to try to provide a finite different discretization of the fractional system in such a way that all of these properties are satisfied. So we're going to talk about the discrete model. And the discrete model, the discretization, is going to hinge on the use of fractional center differences, which were introduced by Otigata some years ago. So fractional center differences for a function f of order alpha are going to be defined as this double series where the constants g are given by this expression, and they satisfy these properties. Moreover, if f is sufficiently regular, then this discrete operator approximates this continuous operator with order of consistency squared. So we introduced the usual notation for discretization. So we're going to consider a bounded domain in space and time. We're going to provide uniform discretizations. The capital letters are going to be numerical approximations to the lowercase letters. Okay. And we are going to introduce some norms and inner products in the discrete case. Okay. So we introduce also some discrete operators. So these are traditional operators, and we are going to use some compact operators to approximate certain quantities in our model. Okay. We also consider this reduced form of fractional center differences, and we are going to remember some properties of fractional center differences. So they are negative, operators which are self-adjoint, and therefore there is also a square root operator for these operators. Okay, so this is basically the discrete form of the formula for integration by parts in fractional form, and these are some bounds for these operators. The finite difference model that we're going to use in order to approximate the double fractional system is this model that we have here. Notice that these are the forms in which we are approximated the fractional derivatives, and we are going to impose initial and boundary data also. There is an energy expression associated, which is this quantity here. And what we're going to show is that this quantity is conserved and the solutions are bounded exactly as in the continuous case scenario. Okay, we need various calculations. So this lemma introduces various calculations, various expressions which are going to be convenient at some point. I'm going to skip the proofs. We are also going to use Young's inequality, which is traditional, classical. And this is our theorem on the conservation of energy. So if U and M are solutions of the discrete model, then the quantities that I presented before, namely these ones here, are going to be non-negative and are going to be constant throughout time. So notice that this is the discrete form of the conservation of energy theorem for the continuous system. Okay, the proof is relatively simple. It uses these expressions. And to bound the energy from below, we're going to use Young's inequality. Okay. As a corollary, we have the boundedness of the solutions, of the numerical solutions. So there exists a constant C star with the property that all of these quantities are bounded throughout time. Okay. So in order to provide the proof, we are going to use the energy. We have to use the energy, which is conserved, and also we use Young's inequality in various forms. Okay, for the existence of solutions, so the system is linear and it can be expressed in matrix form. To that end, we introduce these matrices C and D. Okay, we notice that the matrix A, which is here, is strictly diagonally dominant. So the proof is straightforward. And the only thing we have to do is to establish basically that definition is satisfied. As a consequence of this lemma, it follows that A is non-singular. So in other words, the inverse exists. Okay, so we introduced more notation. Okay. This lemma introduces various identities which are useful and various inequalities which are also used throughout. In order to establish the solution, the existence of solutions, we need the Le-Raychauder fixed point theorem, which is classical. And the theorem states that if tau is sufficiently small, then the numerical model is solvable. Now it's interesting because remember that we have two quantities, U and M. For the quantities M, solution of this solution of the system is a consequence of arguments from linear algebra. But on the other case, for the other solution, for the solution U, we need to use the Le-Raychauder fixed point theorem. After various quantities and using the fixed point theorem, we can establish the existence of solutions in addition of using, of course, induction, mathematical induction. About the numerical properties, okay, so the first one is going to be consistency. To that end, we are going to compare these continuous operators with these discrete operators. Okay, the main result, okay, this is a lemma. The lemma states that if U and M are sufficiently smooth, there are constants such that all of these continuous quantities in absolute value have difference with respect to these discrete quantities, which are bounded by constants which do not depend on tau and h. And consistency is just a consequence. So if U and M are sufficiently regular, then there is a constancy such that the difference between this continuous and this discrete operator is bounded by this constant times tau squared plus h squared. This tells you that the method is consistent of second order. Same thing applies in the case of the energy operator. So these Hamiltonians, this is the continuous and the discrete Hamiltonians, are going to be bounded in the infinity norm. And the proof follows easily using the Taylor's theorem. Okay. In order to establish stability and convergence, we need some version of Grunwald's inequality. So this is the discrete form of Grunwald's inequality that we are going to employ. We use this lemma also, which is a very technical lemma. I'm going to skip the proof. Okay. And then we have various interesting results. So we have stability, we have uniqueness, and we have convergence. So stability tells you that if the initial data are sufficiently regular, then the solutions of the numerical model are stable for sufficiently small values of tau. Same thing applies for convergence. So for sufficiently small values of tau, the numerical solutions converge to the continuous solutions with convergence rate to the second order in the L2 norm. Okay. Uniqueness, as you know, it is a consequence of stability. Finally, we have some simulations. So these are some simulations. We obtained solutions for U and M. So remember, U is complex and M is real. So these are the solutions, and this is the energy associated to that case. So as you can see, the energy is constant. Okay. As conclusions of this talk, we proposed a new discrete model with two fractional terms. Associated to this model, we proposed energy quantities. We established the existence of solutions. We proved that the model conserves the energy. We demonstrated the boundedness of the discrete model. We established the quadratic consistency of the model. And we proved the stability, uniqueness, and convergence of the model. Okay. For future work, we intend to implement all the models computationally and compare them. That means there are other models available in the literature, and we are going to compare them computationally, numerically, and for efficiency. We are going to analyze the solutions of the continuous model, and we're going to try to study some physical applications. Finally, I would like to thank the organization of this event for allowing this talk, and also the University of Guadalajara in Mexico. And these are just some references which have been useful in the development of this investigation.